Multi-level page tables. A different approach doesn't rely on segmentation but attacks the same problem. How to get rid of those invalid regions in the page table instead of keeping them all in memory. So this is a different implementation than segmentation. We call this approach a multi-level page table, as it turns the linear page table into something like a tree. So instead of segmentation, where we segment all the different code type, like code, heap, and stock, we create a tree data structure. So again, this page table is just a data structure. This approach is so effective that many modern systems employ it, like x86 in your Intel i7 or Intel OS. The basic idea behind the multi-level page table is simple. First, chop up the page table into page size units. Then, if an enter page of page table entries is invalid, don't allocate that page of the page table at all. So we first chop the page table like this in a multi-page table into a fixed size like 1001. If it's not valid, we will not allocate table for it. To track whether a page of the page table is valid, and if valid, where it is in memory, use a new structure called the page directory. So to track this validity, we will create a new structure or a new tree structure, which is called page directory. To fix it first in a fixed page table, and to track if it's valid or invalid. The page directory can be used to tell you where a page of the page table is. So this page directory also tells you where is the page of the page table is. So what is the physical address of that page of the page table is, or the entire page of the page table, or that the entire page of the page table contains no valid pages, because again it talks whether it's valid or invalid. So this like this, you have 1 and then 201, you have the page table for that 201 PFN. So it lets you track the page of that page table in the physical frame. So here the left is a linear page table. So as you can see, that is a kind of like two nested tree. So this is the implementation of multi-level page data structure. On the left of the figure is the classic linear page table. Even though most of the middle regions of the address space are not valid, we still require page table space allocated for those regions. So in linear page table, we have page allocated for this region. Unlike here, we only allocate page for a page table that is valid. So we only allocate physical memory for a page table that is valid. We use a two-level deep page directory data structure. So again, we still require page table space for these regions in linear page table, the middle two pages of the page table. The page directory marks just 2 pages of the page table as valid, the first and last, here 1 and 1. Just those 2 pages of the page table resides in memory, and thus you can see one way to visualize what a multi-page multi-level table is doing. It just makes part of the linear page table disappear, freeing those frames for other uses. So in segmentation or in page based table data structure, we divide its pages for each frame. Now in this, we added another layer in tree where we track first what is valid to be allocated with when it comes to page table, and then we free the frames for unallocated. So in linear page table, this is how we create the page style data structure, but it's still inefficient. So to make it efficient, we make this middle part disappear. We create a page directory structure, freeing those frames for other uses, and tracks which pages of the page table are allocated. With the page directory. So here is the pages of the page table that is allocated with the page directory. So this is the visual representation of that. The page directory in a simple 2-level table contains one per page of the page table. So the page directory is a simple 2-level like this, and it contains one entry per page of the page table. So this is the page of the page table, and it contains one entry in this page directory. A PDE it consists of a number of page directory entries. So a page directory consists of page directory entry, which is the entry to this page of the page table. So a PDE minimally has a valid bit and a page frame number similar to PDE, which we discussed in the previous video. So a valid and a page frame number of the page table. So that's what it is. However, as hinted above, the meaning of this valid bit is slightly different. If the PDE is valid, it means that at least one of the pages of the page table that the entry points to via the PFN is valid. Again, however, as hinted above, the meaning of this valid bit is slightly different. So the meaning of valid here is slightly different from the meaning of valid in the actual page table entry or in our actual page table of the memory, where we track the allocated space for the processes. If the PDE is valid, it means that if the PDE or page directory entry is valid, it means that at least one of the pages of the page table that the entry point to via the PFN is valid. So as at least one of these pages in this page table. So again, it's a page table that contain pages. So as you can see, 3 of them is valid and 2 of here is valid. So it means one of the pages in this page table is valid. So that's what it means, i.e. in at least one PDA on that page pointed to by this PDE. So one of the page table entry pointed to by this PDE is set to 1. So the valid bit in that page table entry is 1. So these are the valid bit in that page table entry. If the fee is not valid equals to 0, the rest of the PDE is not valid. So as you can see, we didn't allocate table here, a page table with pages, with page table entries such as valid here in this first column. So if the PDE is not valid equal to 0, the rest of the PDE is not defined. So again, it's not defined or not allocated. So that's kind of like the high level overview. So how do we create that in code? We will discuss that later. Multi-level page tables have some obvious advantage over approaches we've seen thus far. First, and perhaps most obvious, the multi-level table only allocate page table space in proportion to the amount of address space you are using. So it only allocate page table space which contain the pages, the actual pages that is valid with because in segmentation we have an allocated data. We have an external fragmentation. So we reduce the issue of internal fragmentation in larger page table, but we have the external fragmentation of issue of the segmentation. So here what we are trying to accomplish is we reduce the internal fragmentation. At the same time, it doesn't need us to allocate a contiguous memory, or it reduce the external fragmentation as well, because it's a tree data structure, page directory data structure. So a smaller page table, while at the same time using page directory or multi-level page directory, solve our time and space problem. Thus, it is generally compact and supports sparse address space. So it's compact, it reduces the internal fragmentation while at the same time reducing the external fragmentation. So additionally, remember in the previous video, a tree level is a node data structure. It is not a linear array page table, so, or it's not an array, so we are allowed to have this not contiguous location in memory. So we were able to maximize the space of our limited memory. Second, if carefully constructed, each portion of the page table fits neatly within a page. Making it easier to manage memory. The OS can simply grab the next free page when it needs to allocate or grow a page. So another advantage of this is that each portion of this page table fits neatly into a page, in a fixed size page. If you want to grow the heap, for example, you just need to grab this next page. So it allows for efficiency. You know, you only have few internal fragmentation or few space available with in proportion to your address space, while at the same time giving you a leeway to grow your code. Let's say you ask for malloc or increase of of space using heap. So tip, oh god. To understand space efficiency, to understand time-space trade-offs, when building a data structure, one should always consider time-space trade-offs in its construction. Usually, if you wish to make access to particular data structure faster, you will have to pay a space usage penalty for the structure. So if you want to make it fast, usually or 90+% of the time, you will have to pay for space usage. So here we achieve the balance, like we create this complex data structure for us to achieve the time and space efficiency. Contrast this to a simple non-page linear page table, which is just an array of PT is indexed by VPN. So remember, a page table is just an array of page table entry which has the information for all the page table. So contrast this with that data structure. With such a structure, the entire linear page table must reside contiguously in physical memory. For a large page table, say 4 MB, finding such a large chunk of unused contiguous free physical memory can be a quiet challenge. So again, since that's a linear, we need to allocate a contiguous memory, kind of like in segmentation. So we still have that problem of segmentation, of asking for a contiguous memory. Remember, we have solved that with pages, but then we had some issues with pages, which now led us to innovation of this multi-level page table. So we don't need now a contiguous pages in memory. We just need this data structure or tree that allows us to combine this not contiguous data. So when you're running a process in your system, that data or an application, that data could spread across all your system depending on how your OS manage your memory. With the multi-level structure, we add a level of indirection through use of page directory, which points to pieces of the page table. So the magic of that, the what made that happen is the page directory. It's this 3-level node data structure that allows us to use the valid and the invalid, like a software it's a different from PTE valid and invalid, or the actual page table entry in the physical frame. So again, with such a structure, the entire linear page table must reside contiguously in physical memory. For a large page table, say 4 MB, finding such a large chunk of unused, contiguous free physical memory can be quite a challenge. That indirection allow us to place page table pages wherever we would like in physical memory. So this page table pages, like one we saw earlier, allow us to put that whatever we like in a physical memory, just like this. Here you have this at PFN 12 and then PFN 13 and then PFN 86 and PFN 15. So as you can see here, you have in this 204 PFN, we have 86 and 15. So it's kind of like dispersed like a node data structure. It should be noted that there is a cost to multi-level tables. On a TLB MIS, 2 loads from memory will be required to get right translation information from the page table. One for page directory and one for PTE itself. But there is a disadvantage because we're managing it using a page directory. Therefore, we also need to do 2-page translation. One for page directory and one for the actual page table itself. But the advantage is that we can disperse that memory wherever we want to place it in memory. Thus, allow us to solve the problem of external and internal fragmentation. In contrast to just one load with a linear page table, thus the multi-level table is a small example of a time-space trade-off. So we save memory, but we increase the time of translation. But that's not the point. We actually want to save space here. So for that space saving, we are willing to sacrifice this time, a longer time for translation. We wanted smaller tables and got them, but not for free. So since implementing this page table allow us to solve that external and internal fragmentation, we got the space efficiency because we are able to use page directory to disperse those memory allocation of the page table such that allow us to get a small page table for allocated process, therefore save memory. But it's not for free because we need to pay for longer time for translation. Although in the common case TLB hit, performance is obviously identical. So for a TLB hit, the performance is identical with a larger page table because it's still in the TLB. It doesn't do this to longer translation. On a TLB MIS, it suffers from a higher cost with smaller table. Another obvious negative is complexity. Whether it's the hardware or OS handling the page table lookup on a TLB MIS. So another is a complexity. Whether you're gonna use a hardware or OS in handling the page table lookup. So again, what we're doing here is a page table lookup, or we're optimizing the data structure for looking for the page table or for translating the virtual address to a physical frame number. So again, whether it's the hardware OS handling the page table lookup on a TLB MIS, because again, a TLB will expedite that because it's using this cache. Doing so is undoubtedly more involved than a simple linear page table lookup. So it's more complex than the page linear table lookup we discussed in the previous video. Often we are willing to increase complexity in order to improve performance or reduce overheads. In the case of a multi-level table, we make page table lookups more complicated in order to save valuable memory. A detailed multi-level example. Imagine a small address space, 16 kilobytes with 64 bytes size per pages. Thus, we have a 14-bit virtual address space with 8 bits for VPN and 6 bits for the offset. A linear page table would have 2 raised to 8 or 256 entries, even if only a small portion of the address space is in use. So these pages is 64 byte pages. Thus, we have a 14-bit virtual address space with 8 bits for the VPN or virtual private number and 6 bits for the offset. So again, the offset will determine or will help us locate where that exact bit or located in physical frame in this physical frame representation we discussed in the previous video. A linear page table would have 2 raised to 8 or 256 entries. So for a linear page table in this kind of address space, we would have 256 entries, even if only a small portion of the address space is in use. So if you use a linear data structure, we will have 256 entries even if only a small of this in use, like this. First, second page, and then 0, 1, 2, 3, 4, fifth, and then the last one. So 16 kilobytes address space with 64 byte pages. In this example, virtual pages 0 and 1 are for code, virtual pages 4 and 5 for the heap, and virtual pages 254 and 255 for the stock. The rest of the pages of the address space are unused. To build a 2-level page table for the address space, we start with our full linear page table and break it up into page size units. So, in order to create a 2-level or the first multi-level page table, we will start with our linear page table implementation. We start with our full linear page table and break it up into page size units. Recall our table in this example has 256 entries. Assume each PTE is 4 bytes in size. Thus, our page table is 1 kilobytes. So 256 entries times 4 bytes, it would be 1 kilobyte. So that's the size of the page table. Given that we use 64 byte pages, the 1 kilobyte page table can be divided into 16 64 bytes pages. Each page can hold 16 PTEs. So a 64 byte pages could hold 16 page table entry. So out of that 256 entries, one page could hold 16 page table entry. What we need to understand now is how to take a VPN and use it to index first into the page directory and then into the page of the page table. So what we need to understand when creating a multi-level page table is how to take a VPN or virtual private number and use it to index to page directory we discussed earlier and to the page table entry or the page table itself. Remember that each is an array of entries. Thus, all we need to figure out is how to construct the index for each from pieces of the VPN. So, since all of this are array of entry, whether it's page directory or page table entry, all we need is to figure out how to construct the index. So how can we index that from VPN to page directory, from page directory to page table entry for each from pieces of the VPN. Let's first index into the page directory. Our page table in this example is small, 256 entries, spread across 16 pages. So these 256 entries are spread across 16 pages. Why? Because in 64 bytes, we can only hold what's that? Where is that? 16 PTEs. So 256 divided by 16, that would be 16 pages. Let me check. Yeah, that's 16 pages. So to index this page directory, we're gonna use that knowledge that for the 256 entries, we will need a 16 page table. So the page directory needs one entry per page of the page table. Thus, it has 16 entries. As a result, we need 4 bits of the VPN to index into the directory. We use the top 4 bits of the VPN as follow. So in this vid, as you can see, we need 4 bits of VPN to index into the directory. So to get the directory from VPN to page directory to page table index, we're gonna use 4 bits to index from VPN to page directory. Once we extract the page directory index for short from the VPN, we can use it to find the address of the page directory entry. So once we get this, we will gonna use that to find the address of the page directory entry. Again, page directory index is different from page directory entry with a simple calculation. So PDE address equals to page directory base plus PD index times size of PDE. So this result in our page directory, which we now examine to make further progress in our translation. So this translation will result in the actual page directory entry address, which will help us to translate to page table entry. If the page directory entry is marked invalid, we know that the access is invalid and thus raise an exception. If, however, the PDE is valid, we have more work to do. Specifically, we now have to fetch the page table entry from the page of the page table pointed by this page directory entry. So again, let me repeat. This is where the if-else statement will gonna be used. If it's valid or invalid, will determine the further translation. We will see that later. The further access in memory of the translation. It's used if-else statement in the background. I think we could go into that. Where is that? Here, this is how it looks like. We access memory in PDE address. If it's valid, therefore we will do the translation for PDE address. and then we will insert that in the actual TLB, and we will retry instruction. So that's how it looks like in code, but it will start again with TLB. So again, let's repeat this. It's kind of like a complex sentence. If, however, the PDE is valid, we have more work to do. Specifically, we now have to fetch the page table entry. Sorry, we have now to fetch the page table entry from the page of the page table pointed by this page directory entry. So again, this is how it looks like in graph. So we will now need to point there in this PTE to be able to retrieve that or to perform the translation. So again, specifically, we now have to fetch the page table entry from the page of the page table. So from that page table, we will get the page table entry, the one that has valid or invalid bit further down the after the page directory structure table, pointed to by this page directory entry. Remember, on the last table here, we only have few valid bits, not all is valid, so it points that this is the entry point, this is the 0, so it points there, and then it will traverse here and then check if that is, if there is anything valid here. As you can see, it start with the first table, or sorry, first page in this page table. So this is the page table entry that we are talking about here. Again, specifically, we now have to fetch the page table entry from the page of the page table pointed to by this page directory entry. To find this PTE, or to find that earlier, the first page in that page table entry, for that first page in page table, we will have to index into the portion of the page table using the remaining bits of the VPN. So here we have a page table index. So we start with page directory, and now we have this page table index. So it's still part of the VPN, as you can see. So this page table index, PTE index for short, can then be used into the page itself, giving us the address of our PTE. So to find the address of this PTE, we just need to see that to know that it is near this page directory index bit. So 13, the page directory is 13, 12, 11, 10, and then page table index is 9, 8, 7, 6. Now this PTE address is equals to page directory entry dot pfn less than ship plus PTI index, or page table index, times size of page table entry. So these are index, it's different from the entry. We will multiply that with entry to get that actual page table entry address. We got the first page in that page table of the actual physical frame, near the actual physical frame. So note that the page frame number obtained from the page directory entry must be left shifted into place before combining it with the page table index to form the address of the PTE. So we left shift that, or the page frame on obtained from the page directory entry must be left shifted into place before combining it with page table. So from that page directory entry we got earlier, we will be left shifted that with the physical frame. So again, note that the page frame number obtained, or PFN, obtained from the page directory entry earlier, which is the PDE, must be left shifted into place before combining it with page table index, or here, to form the address of page table entry. To see if this makes sense, we'll fill in a multi-level page table with actual values and translate a single virtual address. Let's begin with page directory. For this example, left side 20.5. So here, page directory, we have PFN, physical frame number 100, and the last entry is 101. So as you can see here in this page directory, you have 100 and 101 physical frame at first. So here is the PTE address again, and here is how we get the PTE index here in this formula. In this figure, you can see that each page directory entry, PDE, describes something about a page of the table for the address space. So this 100, is it valid? So if it's valid, so this page directory tells us if that characteristic of the page table in the page table entry is valid or not. So in this example, we have two valid regions in the address space. Now it is located here in the PFN 100 and the 101 in the page directory. In this example, again, we have two valid regions in the address space at the beginning and end, and a number of invalid mappings in between. In physical page 100, the physical frame number of the zeroth page of the page table. So this physical frame number is converted the physical frame number of the zeroth page of the page table. We have the first page of 16 page table entries for the first 16 VPNs. So since we divided 256 into 16 entries for page directory, we have the first page of the 16 page table entries for the first 16 VPNs, which is divided as part of our page directory in the address space. See figure 2.5, middle part, for the contents of this portion of the page table. In physical page 100, the physical frame number in the physical page 100, the physical frame number of the zeroth page of the page table, we have the first page of 16 page table entries for first 16 VPNs in the address space. This page of the table contains the mappings for the first 16 VPNs. In our example, VPN 0 and 1 are valid. So in this 16, it is also divided in 16. So 0 and 1 is valid from this first part. The code segment as are 4 and 5. So within this physical frame number of page directory, we also have the 4 and 5 as valid in this 16 entries, or which is the heap. Thus the table has mapping information for each of those pages. So this table or page this 16 page table has a mapping for these actual pages. So again, we have this first in page directory 100, we got is as valid, and it maps to this another 16 entries which have 0 1 and then 4 5 as valid, and it also has this protection, which another of its characteristics. Again, thus the table has mappings for information for each of those pages. The rest of the entries are marked invalid. So these rest of the entries again are marked invalid, just like uh, um, here in the page directory. So again, this is just like a larger picture of the representation we discussed earlier. This is the page, or the 16 bytes, 64 bytes with 16 entries um, for the actual page table. Okay, so as you can see, we have two here. So we just graph or represent that in different way: a page directory and pieces of page table. So the other valid page of the table is found inside 101, PFN 101. So this page contains mapping for the last 16 VPNs of the address space, seat 20.5 right. So this is the last 16 VPNs of the address space. As you can see, we only have the last part as a valid. In this example, VPN 254 and 255. So this represent 254 and 255 in this 256 entries, because again it starts with 0. The stock have valid mappings. Hopefully what we can see from this example is how much space savings are possible with a multi-level index structure. In this example, instead of allocating the full 16 pages, which is here, in 256 entries we have 16 pages, we only allocate 2 pages, or 3 pages to be exact. For a linear page table, we only allocate 3, which is 1, 2, and then 3 for the actual translation to a page table, or the actual page table. So this is where we get the actual page table here, PFN 10, PFN 23. So we convert that from 100, we get 10, 23, 80, 59 as a physical frame, and then 50, 45. 1 for the page directory, 2 for the chunks, 1 for the page directory, which is the 16 pages, and 2 for the chunks of the page table that have valid mappings. So the other pages was again in this page table structure, a page one page could contain this page table, an entire page table, which makes it a small page table efficient, because we can since it can be contained in one page size, that page table of the actual page table directory. We are only we're able to allocate just that size. So as you can see, we still have this. So in case we need to grow it via heap, we still have the free space, and we have a smaller page table, kind of like a small page table allocated with a goal of reducing external fragmentation, while at the same time reducing internal fragmentation, while at the same time having some free space for growing the heap, okay, and stock. So the savings for large 32-bit or 62-bit address space could obviously be much greater. So it's just for 16-bit pages or address space, but it will be more for a large address space. Okay, so finally, let's use this information in order to perform a translation.
So how do we convert this to converted page table into actual physical address? So here's an address that refers to 0th byte of the VPN 254, 0x3f80, or 11, then 1111, then 1000, then 0000 in binary. Recall that we will use the top 4 bits of the VPN to index into the page directory. So these top 4 bits will be indexed to the page directory, thus 1111. We'll choose the last 15th. If you start at the 0 entry of the page directory above, this points us to a valid page of the page table located at address 101. So here 101. So that's the 111 representations in binary. So so again, 0th byte of VPN 254 is 0x3f80 or 1110 in binary. So those first 1111 will point to 101, right? So we didn't use the next 4 bits of the VPN 1110 to index into the page of the page table, which is here. Here. This is the page, and then it was represented in different way earlier. So PTE address equals to PDE.pfn and then shift plus the PTI index time size of PTE. So that's how we get the PTE address or the start of that page table for the actual page. In the next to last 14 entry on the page, 1110 is the next to last. Entry on the page and tell us that page 254 of our virtual address space is mapped at physical page 55. So this 1110 is the next to last or 14th entry on the page. So here's the physical address equals to pte.pfn shift. So this is where we convert it to the actual physical address. pte.pfn, we ship it plus the offset. So this 1110 is the page table entry, which will determine our physical address and tell us that the page 254 of our virtual address space is mapped at physical page 55. By concatenating fm equals to 55 or hex 0x37 with offset 0000, which is the last digits here, 1, 2, 3, 4, 5, 6. We can thus form our desired physical address and issue the request to the memory system. So here's the physical address, pte.pfm shift plus offset. So you should now have some idea of how to construct a two-level page table using a page directory which points to a pages of the page table. So this page directory point to the page of the page table of the actual physical address. Unfortunately, however, our work is not done. As we'll now discuss, sometimes 2 levels of page table is not enough. Now more than 2 levels. In our example thus far, we've assumed that multi-level page table now have 2 levels. A page directory and then pieces of page table. In some cases, a deeper tree is possible or a deeper node structure. Let's take a simple example and use it to show why a deeper multi-level table can be useful. In this example, assume we have 30-bit virtual address space and a small 512-byte page. So now we have 30-bit virtual address instead of 16 virtual address, and a small 512-byte page instead of 64. I think we have 64 bytes earlier. Yeah, we have a 64-byte size pages. Now we will have 512 bytes, so it's bigger. Thus, our virtual address has 21-bit virtual page number component and a 9-bit offset with 30-bit virtual address space and 512-bit page. Remember our goal in constructing a multi-level page table to make each piece of the page table fit within a single page. So the goal in constructing this is actually to make each piece of the page table fit within a single page. So here, like this, a single page table will fit in the single page instead of multiple pages. Thus far, we've only considered the page table itself. However, what if the page directory gets too big? So we only consider this page. So what if this gets big? Thus far, we've only considered the page table itself. What if the page table gets too big? To determine how many levels are needed in a multi-level table to make all pieces of the page table fit within a page, we start by determining how many page table entries within a page. So again, to determine how many levels are needed in a multi-level table to make all pieces of the page table fit within a page, we start by determining how many page table entries fit within a page. So to be able to like fit that in a page table, in a one page, those page table, we start by determining how many page table entries fit within a single page. So these are page table entries, right? So how many of that is fit within a page? And also that's what we use to get that actual or to translate from page directory to page table. We start with the first page table entry. So here, page table address, entry address equals to PDE or page directory entry dot page frame number, and then we shift that plus page table index times size of PTE or page table entry. Given our page size of 512 bytes, assuming a PTE size of 4 bytes or page table entry size of 4 bytes, you should see that you can fit 128 PTEs on a single page. So if you have PTE size of 4 bytes
and a page size of 512 bytes. Therefore, in a single page, we have 128 PTEs, or 128 of this level. When we index into a page of the page table, we can thus conclude we'll need at least the least significant 7 bits, or log 2128 of the VPN as an index. So given that size, we can thus conclude we'll need at least 7 significant bits here. So this page table index, or PTE index for short, can then be used to index into the page table itself, giving us the address of our PTE address pde.pfn ship. So page directory index here in VPN, and page table index. So again, given this 512 bytes and assuming PTE size of 4 bytes, you should see that you can fit 128 PTEs on a single page. When we index into a page of the page table, so when we index that into that page of that page table, we can thus conclude we'll need a least significant 7 bits, or log 2128 of the index. So once we extract the page directory index, or PDI index here for short, from the VPN, we can use it to find the address of the page directory entry. So once we get this page directory index until 1, 2, 3, 4, 5, 6, 7, we can use that to find the address of page directory in entry with a simple calculation. So this is how we get the page directory entry, or this page directory entry for a larger pages. So we get the index first. So PDE address equals to page dir base plus PDI index times size of PDE. So this results in our page directory, which we now examine to make further progress in our translation. So aside starting point of virtual address, so from the text, virtual address equals to 30 bits total. Offset is 9 bits, since page size equals to 512 equals to 2 raised to 9. Now VPN, virtual page number, equals to 21 bits, since 30 minus 9 equals to 21. So to get the VPN, we minus that from the offset. Now, how do we divide that 21 bits from that virtual address space? Now, page table index, each page table entry is equals to 4 bytes. So that's the actual entry from the actual page table. So this is the one we use to manage the actual pages in the actual physical frame. So a single page equals to 512 bytes. So each page table can hold 512 over 4 equals to 128 entries. So which needs 7 bits. So page table index is equals to 7 bits. Leftover VPN bits is equals to 21 minus 7 is equals to 14. Now we only have 14 VPN left, or 14 bits in the address space, since we need this 7 bits for page table index. Now, where do those 14 bits goes? These 14 leftover VPNs are what the text is talking about in the line you highlighted. So when you also might notice from the diagram above is how many bits are left into the large page directory, which is 14. If you only have one page directory level, just 17 bits wide, or 128 entries, since we need to make the page table to fit in a pages, so we only have 128 entries. It wouldn't be able to cover the full 14 leftovers VPN bits. We still have 7 bits remaining. That's why they split it up, so the page directory into multiple levels. That's why we will split that into multiple levels. So step 3, splitting the page directory. To manage the 14 leftover VPN bits, we divide it to PD, or page directory index 0. So that's the first index from page directory, which has 7 bits. PD index 1 is equals to 7 bits, so that's the next level. And then the actual page table index, or page table entry, which is the 7 bits. Now the offset is 9 bits because it has a 512 bytes sizes. Now the enter 20 byte 1 bit VPN is accounted for. 7 plus 7 plus 7 equals to 21. So the 14 bits left are simply the top 14 bits of the VPN. Bits 20 down to 7. Those are the ones not used by the first page table index. Since a single 7-bit page directory can cover them, you need 2 levels of the page directory. So we need 2 levels of page directory, or PD0 and PD1, each consuming 7 bits because it has 128 entries, and we need to fit that this page table on the size of our pages, since 7 bits has 128 entries, or 512 bytes. So in other words, first 7 is equals to page table index, remaining 14 require 2 levels of page directory, which is 7 plus 7. So again, what you also might notice from the diagram is how many bits 14 are left into the page directory 14. If our page directory has 2 entries and a 4-byte PDEs, our page directory entry spans not 1 but 128, and our goal of making every piece of multi-level page table fit into page vanishes. So to remedy this, we build a further level of 3. So PD 0, PD index 1, and PD page table index. By splitting the page directory itself into multiple pages, and then adding another page directory on top of that to point to the pages of the page directory. We can then split up our virtual address as follows: PD index 0, PD index 1, page table index. Now, when indexing the upper level page directory, let's explain this further. So why not just use 14 bits at once? So if you wanted to use all 14 leftover bits in one step, you need a single page directory with 2 raised to 14, or equals to 16,384 entries to be able to use that. So each entry is equals to 4 bytes, because each PD is equals to 4 bytes. That would make the page directory size 16 times 384 times 4 equals to 536 byte. But this doesn't fit inside a single 512 bytes. Remember, the whole goal is that each paging structure, PT, or page table, page directory, etc., fits inside one page. That's what keeps the design clean and efficient. The 7-bit limitation. So here's the reason why we use 7-bit. The reason each level, page table, page directory, etc. is 7 bits is not arbitrary. It comes from the fact that one page is 512 bytes equals to 2 raised to 9. Each entry is 4 bytes equals to 2 raised to 2. So one page can hold 2 raised to 9 minus 2 equals to 2 raised to 7 equals 128 entries. To pick one of 128 entries, you need 7 index bit, which is that raise to 7. That means any level that fits inside a single 512 byte page can only ever consume 7 bits of the VPN. So again, any level that fits so one page can hold 2 raised to 9 from that 512 byte minus 2 raised to 2 from that 4 bytes equals to 128 entries. So to pick one out of 128 entries, you need 7 index bits. That means any level that fits inside as a single 512 byte page can only ever consume 7 bits of the VPN. So again, any level that fits inside a single 512 byte page can only ever consume 7 bits of that VPN. So that's what we get, this 7-bit limitation. So each level add, whether it's a page table, page directory, or another directory, uses exactly 7 bits. The solution, break 14 into 7 plus 7. Since one page can only give you 7 bits worth of entries, those 14 leftover bits are split into two 7-bit indices. PD index 0, 7 bits, select one page of the second level directory. PD index 1, 7 bits, select the final page table. Page table index 7 bits, select the actual page table entry. Or now each structure fits neatly into 512 byte page. So again, since one page can only give you 7-bit worth of entries, those 14 leftover bits are split into two 7-bit indices. So these are the first entry, which is the actual index. Now we have PD index 0, page directory index 0, select one page of the second level directory. And then the PD index 1 has 7 bits as well, selects the final page table of the actual page table index. And then selects this page table index, selects the actual page table entry. Now each structure fits neatly into a 512 byte page. Big picture. So the full breakdown of the 21-bit VPN is 7 bits PD index 0, top level directory, 7 bits PD index 1, second level directory, 7 bits page table index, page table, 9 bits offset inside the page, total 30-bit virtual address space. So that's the 9 bits offset, which again came from the 512 bytes size. Each level equals to 7 bits because of 512 byte page size and 4 byte entries. You can't use 14 bits in one directory because that would require 64 kilobytes for the directory, too big for one page. Therefore, the 14 bits must split into two 7-bit chunks, giving you two directory levels. So to remedy this problem, we build a further level of the tree by splitting the page directory itself into multiple pages. So we split further the page directory into multiple page and then adding another page directory on top of that to point to the page of the page directory. We can then split our virtual address as follows. So PD index 0, PD index 1, and then the actual page table index that points to actual page table entry. So that's why the formula for page table entry requires the page table entry address requires the index, because we need to get the page table index in this multiple level. Let's just put that. So that's why the formula for the actual page table entry address requires us the PDE and the page table index. So this is how it looks like in its VIT form. Again, we calculate that VPN and we add the offset to convert that into actual physical address. Now, when indexing the upper level page directory, we use the very top bits of the virtual address, PD index 0 in the diagram. This index can be used to fetch the page directory entry. So again, PD index 0 in the diagram. This index can be used to fetch the page directory entry or PDE entry from the top level page directory. So let me repeat. Now, when indexing the upper level page directory, we use the very top bits of the virtual address, PD index 0 in the diagram. This index can be used to fetch the page directory entry, or this index 1, from the top level page directory. So if it's valid, the second level of the page directory is consulted, combining the physical frame number, or this PDE, combining this physical frame number from the top level PDE and the next part of the VPN or PDE index 1. Finally, if valid, the PDE address can be formed by using the page table index combined with the address from the second level PDE. Ooh, that's a lot of work and all just to look something up in a multi-level table. So to get that the actual physical address, we get this PDE dot PFN and then shift plus this offset. So first we check if it's valid here. If it's valid, we check here, and then we check here, and then if it's still valid, then we get that VPN, and then we add it with the offset. So physical address. So this is where it looks like physical address. Where's the physical address here? TBL entry. Here, the PDE address is PDE.PFN and then shift plus PDE PTI index size of PTN. And then the PTI index is equals to VPN and PT mask PT ship. So this is the formula if it's valid. And then the PDE address, these are the formula for that: base plus index plus size of PDE, and then PDI is index is VPN and PD must and then PD shift. So this is how we get the first directory or PDI index. And then here is the page table index. So the translation process, remember the TLB. To summarize the entire process, the translation using a two-level page table, we once again present the control flow in algorithmic form, figure 20.6. The page shows what happens in hardware, assuming a hardware managed TLB upon every memory reference. So VPN first equals the virtual address and VPN mask greater than ship. Then line 2 success comma TLB entry equals to TLB lookup VPN if success equals to TLB equal true TLB hit if can access TLB entry that protected bits equals to true offset equal virtual address and offset mask. And then so that's the offset if can access TLB entry that protected bits equals to true
Offset equals to virtual address and offset mask. Physical address equals TLB entry.pfn less than shift offset. Register equals to access memory physical address. So else raise exception protection fault. Else first this is the comment. First get page directory entry PDI index equals to VPN and PD mask greater than PD ship, and then PDE address equals to PD base page directory base plus index PDI index plus time size of PDE, and then PDE is equals to access memory page directory entry address. If PDE.valid is equals to false, raise exception segmentation fault. So first is the protection fault, now segmentation fault. Else if it's valid, PDE is valid, now fetch PDE from page table. PTI index is equals to VPN and PT mask greater than PT shift. PTE address equals to PDE dot PFN less than shift plus PTI index times size of PTE. PTE is equals access memory PTE address. If PTE.valid equals to false, raise exception segmentation fault again. Else if can access PTE.protection bits equals to false, raise exception protection fault. Else TLB insert with the parameter VPN comma PTE.pfn comma PTE.protection bits. Then retry its instruction. As you can see, we insert a VPN, PTE.pfn, and PTE.protection bits in TLB before we retry instruction. As you can see from the figure, before any of the complicated multi-level page table access occurs, the hardware first checks the TLB. Upon a hit, the physical address is formed directly without accessing the page table at all. As before, only upon a TLB miss does the hardware need to perform the full multi-level lookup. On this path, you can see the cause of our traditional two-level page table, two additional memory access to look up a valid translation, inverted page table. So this is here, instead of having many page tables, one per process of the system, we keep a single page table that has an entry for each of the page of the system. The entry tells us which process is using this page and which so this entry tell us which process is using the page and which virtual page of the process is using the physical page. So that's an even more extreme space saving in the world of page table. So instead of having many page table, one per process of the system, we keep a single table that has an entry for each physical page of the system. The entry tells us what process is using this table, these pages, and which virtual page that process maps to the physical page. Finding the correct entry is now a matter of searching through this data structure. A linear scan would be expensive, and thus a hash table is often built over the base structure to speed up lookups. So it uses a hash table. It doesn't know the no data structure. An example is the PowerPC. So use that such architecture. More generally, inverted page tables illustrate what we've said from the beginning. Page tables are just data structures. You can do lots of crazy things with data structures, making them smaller or bigger, making them slower or faster. Multi-level and inverted page table are just two examples of the many things one could do. So this multi-level, it's still a multi-level page table, but it's inverted and it uses a hash table. Just two examples of the many things it could do. So let me retract in this. I intentionally keep this. So be wary of complexity. System designers should be wary of adding complexity into their system. What good systems builder does is implement the least complex system that achieves the task at hand. For example, if this space is abundant, you shouldn't design a file system that works hard to use as few bytes as possible. Similarly, if processors are fast, it is better to write a clean and understandable module within the OS than perhaps the most CPU optimized hand assemble code for the task at hand. Be wary of needless complexity. In prematurely optimized code or other forms, such approaches make systems harder to understand, maintain, and debug. As Antoine de Saint-Exupéry famously wrote, perfection is finally attained not when there is no longer anything to add, but when there is no longer anything to take away. What he didn't write, it's a lot easier to say something about perfection than to actually achieve it. And there's a so when building a data structure, one should always consider time-space trades-off in its construction. Usually, if you make like that hash table, if you wish to make access to particular data structure faster, you will have to pay a usage penalty for that structure. So that what the inverted page table does to us. So it allows us to access it faster, but at the same time, it access more memory. So swapping the page tables to disk. Finally, we discuss the relaxation of one final assumption. Thus far, we have assumed that page table reside in kernel-owned physical memory. So the kernel-owned physical memory is where the process are located in the actual memory that your operating system resides, because remember, it takes over or it guides all those processes to be able to keep everything safe and easy to use and provide the illusion of ease of use. Even with our many tricks to reduce the size of page tables, it's still possible, however, that they may be too big to fit into memory all at once. Thus, some systems place such page table in kernel virtual memory, thereby allowing the system to swap some of this page table to disk when memory pressure gets a little tight. So some systems place such page table instead of the actual OS physical memory in its virtual memory, thereby allowing the system to swap some of this page table to disk when pressure gets little tight. So instead of putting all of that into physical memory, we put some of that into disk or in its virtual memory. We'll talk more about this in future chapter, namely the case study on VAX or VMS, once we understand how it moves pages in and out of memory in more detail. We have now seen how real page tables are built, not necessarily just linear arrays, but more complex data structures. So we saw how to implement complex or three-way node structure and inverted page table or hash table, to implement multi-level page table, to optimize the space first for node structure and for time for hash table structure. The trade-offs such table present are in time and space. The bigger the table, the faster a TLB miss can be serviced, as well as the converse, and thus the right choice of structure depends strongly on the constraint of the given environment. In a memory constrained system, like many older systems, small structures make sense.
In a system with a reasonable amount of memory and with workloads that actively use large number of pages, a bigger tables that speeds up TLB misses might be the right choice. So again, we have now seen how real page tables are built not necessarily just a linear arrays but a complex data structure. In a memory constrained systems like many older systems, small structures make sense. In a system with a reasonable amount of memory and with workloads that actively use a large number of pages, a bigger table that speed up TLB misses might be the right choice. Again, in a system with a reasonable amount of memory and with the workloads that actively use a large number of pages, a bigger table that speed up TLB misses might be the right choice. For a large, processes that use a large table, a reasonable or a large memory might be the right choice. So that smaller table makes sense, or small structures in a memory constrained system. So the one we implemented earlier could be a right choice for to older system. But if you want to reduce this TLB misses and not care about those internal and external fragmentation, a large memory that could handle those loads would be the right choice. So when software managed TLBs, the entire space of data structure opens up to the delight of operating system innovator. That's you. What new structures can you come up with? What problems do they solve? Think of these questions as you fall asleep and dream the big dreams that only operating system developers can dream. Beyond physical memory mechanisms, thus far we've assumed that an address space is unrealistically small and fits into physical memory. In fact, we've been assuming that every address space of every running process fits into memory. We will now relax these big assumptions and assume we wish to support many concurrently running large address spaces. So before we assume that we're only handling those 16-bit address spaces. Now, we will assume we can handle like 30 to 64-bit at the same time. Thus, the introduction of a hard disk drive or SSD. To do so, we require an additional level in memory hierarchy. Thus far, we have assumed that all pages reside in physical memory. However, to support large address spaces, the OS will need a place to stash away portions of address space that currently aren't in great demand. So anything or any address space that aren't in great demand shall be able to put into the hard disk drive or slow memory. In general, the characteristic of such a location are that it should have more capacity than memory as a result. So the characteristic of that is low, but it has larger than the general memory. It's generally slower. If it were faster, we would just use it as memory. No, in modern system, the role is usually served by hard disk drive. So if it can be larger, we're just gonna use a larger memory. But again, our memory are limited.
are the actual, memory we use, not the slower one or the second level. Or thus in our memory hierarchy, big and slow hard drives still sit at the bottom with memory just above, or the second level. Yeah, so we wouldn't need that second level memory if we have this high level memory, a lot of high level memory, kind of like in the um, physical world or on our biology. If we could like learn everything at once, we don't need to learn that or to memorize things to get into the process of getting habitual and making things second nature. If we have a large memory to understand all of this, unfortunately we don't. So we need to be careful on what we focus on, because we only have limited memory. We cannot understand both, so we need to read every day. One question you might have: why do we support a single large address space for a process? Once again, the answer is convenience and ease of use. With the large address space, you don't have to worry about if there is enough room in memory for your program's data structure. Rather, you just write the program naturally, allocating memory as needed. So, if we have this support for large address space, we don't need to worry um, if there's enough room for program's data structure, or if you have large program if we're creating for this operating system. It is a powerful illusion that OS provides and makes your life vastly simpler. You're welcome. A contrast is found in older systems that memory overlays, which programmers manually move pieces of code or data in and out of memory as they were needed. Try imagining what this would be like. Before calling a function accessing some data, you would need first arrange for the code or data to be in memory. So yuck. So you're gonna write that code. So operating system makes it easier. The process of putting that into the memory is abstracted to you. So all you need to worry is that about the functions. You don't need about to worry about the large virtual address space, or the limited memory that this program consumed. Rather, the OS delete the unused processes by the system, because the actual person using that operating system only process one program, like the memory, to begin with. Beyond just a single process, the addition of swap space allow the OS to support the illusion of large virtual memory for multiple concurrently running processes. The invention of multiprogramming, running multi-programs at once to better utilize the machine, almost demand the ability to swap out some pages, as early machines clearly could not hold all the pages needed by all processes at once. Again, demanded the ability to swap out some pages, as early machines clearly could not hold all the pages needed by all processes at once. Thus, the combination of multiprogramming and ease of use led us want to support using more memory than physically available. So the swap space also allowed this illusion of a large virtual for multiple concurrently running process. So this invention of the multiprogramming, or the multi-thread concurrently running in the for multiple process, demanded the ability to swap out some pages, as early machines clearly could not hold the pages needed by all processes at once. Thus, the combination of multiprogramming and ease of use led us to want to support using more memory than physically available. It is something that all modern VM systems do. So all, even the cloud. So it supports that illusion of large memory by providing this second level memory. Now swap phase. The first thing we need to do is to reserve some space on disk for moving pages back and forth. In operating system, we generally refer to such pages as a swap space because we swap pages out of memory to it and swap pages into memory from it. Thus, we will simply assume that the OS can read from and write to the swap piece. In page size units, to do so, the OS will need to remember the disk address of a given page. So the first thing is to reserve some space on that second level memory to swap page back and forth, and we will call that swap page. We generally refer to such space as swap piece because we swap pages out of memory to it and swap into memory from it. Thus, we will simply assume that OS can read from and write to swap space. So we will assume that there's some code that allow us to read and write on that free space. To do so, the OS will need to remember the disk address of a given page. So to do that, one key is that the OS will need to know the disk address of that space, because you won't be able to swap into it if you don't know the address. So the size of the swap space is important, as ultimately it determines the maximum number of memory pages that can be in use by a system at a given time. So that swap space will determine the maximum pages that the operating or the system can be used at a given time. Let's assume for simplicity that is very large for now. So in the tiny example, figure 21.1, you can see a little example of a 4-page physical memory and 8-page swap space. In the example, 3 processes proc0, proc1, and proc2 are actively sharing physical memory. Each of the 3, however, only have some of their valid pages in memory, with the rest located in swap space on disk. So here we have 3. So it only have their valid pages in physical memory, right? With the rest located in swap space on disk. So those are invalid. A 4th process, proc3, has all of its pages swapped out to disk. So in physical memory, we only have proc0, proc1, and proc3. Proc1 and proc2. For proc3, all of its pages swap out to disk, and thus clearly isn't currently running. One block of swap remains free. So one block of this swap space remains free. Even from this tiny example, hopefully you can see how using swap space allows the system to pretend that memory is larger than it actually is. We should note that swap space is not only on disk location for swapping traffic. For example, assume you are using a program, binary, ls, or your own compiled main program. The code pages from the binary are initially found on disk. When the program runs, they are loaded into memory either all at once when the program starts execution, or as in modern system, one page at a time when needed. However, if the system needs to make room in physical memory for other needs, it can safely reuse the memory space for these code pages. So these ls are the number one program the operating system used to make room for other processes, because it can safely reuse the memory space for these code pages. Again, it's just code pages, knowing that it can later swap them in again from on this binary in the file system, whether it's bit by bit or all at once. So in a older operating system. The present bit. Now that we have some space on the disk, we need to add some machinery higher up in the system in order to support swapping pages to and from the disk. Let's assume for simplicity that we have a system with a hardware managed TLB. Recall first what happens on a memory reference. The running process generates virtual memory references like for instruction fetches or data accesses, and in this case the hardware translate them into physical address before fetching the desired data from memory. So again, the running process generates virtual memory reference or VPN for instruction fetches or data access, or whether it's loading the instruction then activating it, or for data access. And in this case, the hardware translate them or these virtual references into physical address before fetching the desired data from memory. If the VPN is found in the TLB, like a TLB miss is not found in a TLB or TLB miss, the hardware locates the page table in memory or in a physical memory using the page table register and looks up the page table only page table entry for this page using the VPN as an index. So it finds the PTE using the VPN as an index again, and we add the offset there, right? If the page is valid in this page table entry and present in physical memory, the hardware extract the PFN from the PTE or the physical frame number, install it in the TLB and retries the instruction, this time generating a TLB hit. So far so good. If we wish to allow the pages to be swapped to disk, however, we must add even more machinery. Specifically, when hardware looks in the PTE, it may find the page is not present in physical memory. Again, when the hardware looks in the PTE or page table entry, it may find that the page is not present in physical memory. So sometimes on that PTE, on that look of a page table entry, it may find that the page is not present, because that determine, or the page table entry will determine if the page physical frame number is valid, protected, or present. The way the hardware or the OS in a software managed TLB approach determines this is through new piece of information in each page table entry known as present bit. So this is the present bit already available in the hardware, just like we discussed in the previous video. If the present bit is set to 1, it means that the page is present in physical memory and everything proceeds as above. If it is set to 0, the page is not in memory but rather on disk somewhere. The act of accessing a page that is not in physical memory is commonly referred to as page fault. So the act of accessing that page that is not in memory but can be accessed on disk is called a page fault. A page fault in the OS is introduced to service the So upon a page fault, the OS is invoked to service the page fault. A particular piece of code known as page fault handler runs and must service the page fault as now described. Aside, swapping terminology and other things, terminology in virtual systems can be a little confusing and variable across machines and operating system. For example, a page fault more generally could refer to any reference to a page table that generates a fault of some kind. This could include the type of fault we are discussing here, like page not present fault, but sometimes can refer to illegal memory accesses. Indeed, it is odd that we call what is definitely a legal access to a page map into virtual address space of a process, but simply not in physical memory at that time. A fault at all. Really, it should be called a page miss, but often when people say a program is page faulting, they mean that it is accessing parts of its virtual address space the OS has swapped out to disk. We suspect the reason that this behavior become known as fault relates to the machinery in the operating system to handle it. When something unusual happens, like when something the hardware doesn't know how to handle occurs, the hardware simply transfer control to the OS, hoping it can make things better. In this case, a page that a process wants to access is missing from memory. The hardware does the only thing it can, which is raise an exception, and the OS takes over from there, as this is identical to what happens when a process does something illegal. It is perhaps not surprising that we term the activity fault, page fault. Term the activity a fault.